a brief introduction about the club. We are the Year of the Computer Vision Club. This is a paper breakdown series where we will be explaining high-level concepts in machine learning from ground up. Today, I'll be covering reinforcement learning. This is a brief summary of what exactly is covered in reinforcement learning, where we have an agent at a particular state taking a particular action affecting the environment and therefore receiving a reward as part of the action that it takes in the environment. So we're sponsored by GitHub. You can you scan the QR code in order to get some free goodies. Yeah, that's it. So, like I said, reinforcement learning is a form of sequential decision making, where an agent observes the world, takes certain actions, which would affect the future possibilities of the agent. After it takes the action, its state changes from one state to the next state, and it receives reward as part of the action that it takes. And the goal of reinforcement learning is to find the optimal policy which can generate the maximum reward as a sequence of the action that it takes. So this can be seen in this slide, where we have the dog, which is the agent. This is the environment, and the goal of the dog is to fetch the wooden stick after it has been thrown. It performs an action, receives a reward as a result of the action it performs, and it observes the state in which it is in after it performs certain actions.
What do you mean by policy?
Okay. So policy is actually a function. So the policy takes in the state that it is in, performs an action and returns an action that will perform in a particular state. So it's just a function of the current state, and it returns the action that will perform if it is in a particular state.
So kind of like a trained agent.
Yeah. So this, so first let's look at this slide, which will properly explain everything. So first, we have an action that is performed as a result of the policy pi, which is conditioned on the state that it is in currently. So the action can be stochastic in nature. Sorry, it can be stochastic in nature, dependent on the state that it is in. So the agent performs an action which results to some state st plus 1. And as you can see, the state st plus 1 not only depends on the current state that it is in, but also the action which it has taken on the state st in order to reach st plus 1, which is pretty obvious. After it reaches st plus 1, depending on how favorable reaching st plus 1 is, it receives a reward RT, and this reward is conditioned again on the state that it is in and the action that it performs. So this is a brief summary of the various definitions that are involved in this case. Going back, I'd like to explain the environment in which we are operating. The mathematical model we are working on is known as a Markov decision process. So this is a discrete time stochastic process. Now, what does this mean? You can think of it as just a series of random variables, x1, x2, all the way up till xn, let's say, where because we are working on natural numbers, it is discrete. And it's a stochastic process because it is just a bunch of random variables. That's what a discrete time stochastic process means. So right now, the agent is at a particular state, chooses an action, puts it into the next state as prime. And this, as has been stated in this slide, depends on a probability function, the action that it performs. And then it receives a reward corresponding to the action that it takes at a particular stage. So this is a Markov decision process, and this is the mathematical model we'll be working in right now. Again, if you guys want to look at this is just a summary of the Markov decision process. Okay. Right. So mathematically, a Markov decision process consists of 5 tuples, the set of states, the set of actions, the probability function for the action, the reward probability function, and the discount factor gamma. So S is the total number of states which the agent can be in, and this is known as the state space. A denotes the set of actions that are possible at each stage. This is known as the action space. PA is the probability that one particular action is taken at a particular state at time t, which would lead to the next stage at time t plus 1. RA is the immediate reward that it receives at the particular time t at a particular stage, and this causes the transition to the next stage. Gamma denotes the discount factor. To understand gamma properly, gamma basically discounts the future rewards because the agent would be taking actions right now and would be taking actions in the future as well. So, and it would be receiving rewards in the future. And our goal is to somehow take into account the future rewards that the agent receives along with the current reward that it has received. So based on the problem that we're trying to solve, the future rewards might not be as important as the immediate rewards. So we would multiply the future rewards by a factor of gamma in order to take into account how important the future rewards are. So to write this out mathematically, if R0 denotes the first reward at the current stage, then we'd multiply it by a factor of gamma in order to get the next reward, followed by a factor of gamma again in order to get the next reward, and so on. And this would be the total reward function that we would be working in right now. And this is the main goal of reinforcement learning. So this summarizes what a Markov decision process is mathematically. Right. So this would help you understand it in a much better way. The yellow circles denote the states in the Markov decision process. There are 3 possible states in this case: S0, S1, and S2. And like I said, there can be several actions which can lead from one state to the next state. In this case, we have A0, which would lead it from, let's say, S0 to S2. A1 would also lead it from S0 to S2. And this action also leads it from S2 to S1. The reward in this case is the -1 and the +5. Plus denotes a reward which is more favorable compared to a -1, which is less favorable. The fractions in this case denote the probability, which would denote how probable it is to take the following action. And yeah, this helps you visualize what exactly a Markov decision process is in this case. So like I said, I've been talking about policy a lot. Let's try and understand what exactly is a policy. So, so the policy is the action that is chosen by the agent at a particular stage. This can be of 2 types. It can be either stochastic or it can be deterministic. In the case of a deterministic policy, at each particular stage, there's only one possible action that the agent needs to take. And therefore, it's just a function from the state space to the action space. Because in this case, we are not working with probabilities at all, right? Whereas in the case of a stochastic probability, it is a probability density function that we need to be working with, because at each stage, the agent can take a multitude of actions. So we'd be working from the state space to the probability space of the set of actions that are possible. And this is conditioned on the state that the agent is in currently. So to summarize, stochastic policies are for probabilities, deterministic policies are for a fixed action the agent can take at a particular stage. Right. What do you guys think would be an example of where we can use deterministic policies? Anyone?
Like a constraint,
Would
set by whoever is training.
like
Something extended training.
because there's only one action possible at each.
I mean, not just one action, but you can say there comes a pedestrian in front of you. And, you just want to take one action. Stop.
Mm-hmm.
You really want to probability.
Right. That makes sense. You also. Oh, you're saying the same thing, right? So yeah, that's one example of deterministic policy. Another example is the game of chess, where at each stage we are just trying to make the best move possible, and it follows under the form of deterministic policy. So we would prefer to use stochastic policies when we need to explore stuff, when it is not so deterministic and there are various ways in which the agent needs to explore the environment, and the environment in which the agent is working is unknown. So that's where we would try and use stochastic policies in comparison to deterministic policies. Yeah. Moving on to the next slide, let's talk about the rewards in this case. So as I said, the agent performs a certain action and receives a certain reward after performing a certain action at a particular stage. So the reward is a function of this state that it is in currently and the action that it has performed, therefore receiving a reward. So the main goal of reinforcement learning would be to take into account the future rewards that the agent receives as well, not only the immediate reward. So there can be two cases. One in which we make use of the gamma, which was the discounted factor, and the other one in which we don't take into account gamma in the case of undiscounted rewards. So as I showed in this equation, we just keep multiplying by the factor of gamma, denoting how less important the future rewards are in comparison to the current reward, which is R naught. Undiscounted rewards are mainly used when all the rewards following R naught are of equal weightage to the agent, are of equal importance to the agent as well. So, right. So an example of when we would want to use undiscounted rewards would be, let's say, when an agent wants to find the shortest path from one point to the other point. In that case, we don't really care about future rewards in this case. Instead, we only care about how long the path is. So at each stage, the reward would be of equal weightage, right? And yeah, that summarizes discounted rewards versus undiscounted rewards. And the main use of discounted rewards is that we are trying to prevent the agent from delaying its own, from delaying it or from making infinite delays, because this factor helps it prevents it from doing that so far. Right. So let's talk about the value function. So the value function is the expected return. this guy here that you can get from this particular state that the agent is at currently. So this can be summarized using this equation, like I said. So we are just trying to get the expectation of the return condition on the agent being at this particular stage. And this just boils down to this one right here, where we are taking into account the value of gamma. And if it's undiscounted, we just put gamma equals 1. So we don't really care about it that much. And right. So this is a value function. And this basically helps you understand how desirable a particular state is. Because the higher the expected return for a particular stage, the more desirable that particular stage is, because the agent would prefer to be in that particular stage with a higher expected return in comparison to a state which has much lower expected return. There's an example which can help you understand this in a much better way. It is this one, right? So the aim of the agent is to start here and end up at the goal. So the agent, do you guys understand why the reward is -1 per time step? Right? Because the main aim is for it to find the shortest path from the start to the end goal. And right, so that's why it's -1 per time step. So the actions would just be north, south, east, west. And the states right now would be either this guy, this guy, this guy, this guy, all the various states that are possible inside this maze, let's say. Right. So in order to, let's say, find the value function of this stage, all we have to do is find a shortest path from the start to the end and just add -1 per step that you take, and you can find the value of this guy right here. So I can just show you one example of a path that can be taken. This is an example of a path from the start to the end. And the red arrows in this case would denote the policy for each stage, because these are the actions that the agent is taking at each particular stage. Right now, I'm just following a deterministic policy for better understanding of what exactly the value function is. So obviously, if the agent starts here and wants to reach here, the shortest path is this one right here. And even though it doesn't explore all of these areas, we're still computing a value function for all of them, because this would lead to something known as exploration versus exploitation. Because even though this is not yet explored, we still might need these areas in the future, because our main aim is to generate the best possible policy, right? So even though these are not explored, we still need these values. Everything clear so far? Oh, you didn't. Okay, sure. This one? Okay. Sure. So we're fixing our policy. You understand what a policy is, right? A policy just takes in the state that it is in, outputs an action that it is. So we are computing the value for a fixed policy right now. The policy right now is pi. Okay. So assuming that the policy is pi, all we're trying to do is compute the expected return. GT out here stands for the return from this particular stage, given the state is S. Right? So like I said, the return from this particular stage is this guy right here, right? So we'd have R0 plus gamma R1 plus dot dot, so on, right? I mean, we can like shift this by time step t if there is no the 0 time step. So that's why we have a plus t out here. And like I said, we're just summing this guy from 0 all the way up to infinity. and we are finding the expected value for this particular policy. Does that make sense now? Anything else?
In your next slide, you said the return is always, rewards is always -1.
Yeah.
But, I believe in your previous slide, the Markov process, slide, you mentioned that the rewards can be different from the action. So why is it rewarding that being always -1?
Oh, why is it always -1? Right. So,
I mean,
So-
it's not, I mean, what I was trying to say is that it's just in this case, it is always -1, but in general, rewards should be a function of action.
yeah, like I said, you can look at this slide. Right. You can look at this slide where I put the reward as a function of the action and the state that the agent is in currently. So
So in this case, it should be the states and the action should be in different instances, or they must be the same.
So, like, we're if
Yeah. So should they be in different instances?
like they're the same because they have to be the same because we have at time t. That's what it means. This just denotes the time step that we're working at right now, the index, right? And going back to why the reward was -1 in this case, the reward is -1 because we want to find the shortest path from the start to the goal. And the more steps we are taking, the worse our reward is becoming, right? So the longer our path, the worse it becomes. That's why it's -1 in this case. Does that make sense?
Yeah.
Right. So we can just compute the value function for this state, let's say. So that'll just be -1, -2, -3, -4, -5, -6, -7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So value function for this guy would be -16. Similarly for this guy, -15, and so on. And we have the value functions for each stage, assuming the policy is deterministic in this case. Right. So these value functions satisfy something pretty interesting known as Bellman equations. And these are extremely useful in the case of dynamic programming. So, right. So like I said, we went from this guy to this guy, then we went to this guy right here. Then we went to this guy. So to get this guy, all we have to do is just take out one term, RT plus 1, just put k equals 0, remove this guy. And then we have the remaining terms. Right. So, right. So after we have this, right, we're taking a particular action at this stage in order to reach the state st plus 1, which is the state s prime that we reach after taking a particular action A. So now we're trying to convert this into something which uses s prime as well, which is the next stage that the agent would be in. So we are conditioning this guy on the agent now being in the state s prime. This, in order to condition that, we need to first find the probability that the state would reach s prime or st plus 1. Oh, sure. Can I? The what? Oh, I can't reach it. So yeah, can you guys see this now?
Yeah.
Okay. So yeah, like I said, we're going to take action A in order to reach the state S prime. So now all we need to do is condition it to the probability of reaching the state St plus 1. This is also very obvious because we're just trying to find the sum of all the actions, conditioning it on the policy and summing all the actions. And we're summing this all up across all the states S prime for all the rewards. And this, and then we have this guy right here. So this should also be pretty intuitive. Does this make sense?
You can talk about why.
Oh, why we want to do this? Because we finally want to use the next state as well as prime, which is used in dynamic programming, in which we are trying to use the value of the next state in order to get the value of the previous state as well. This is used in dynamic programming, and that's why we're trying to do this right now. Does that make sense? Anybody else has any questions?
So like another reason why you can do this is because you want to write the equation as something plus the equation at time t plus 1 so that we can use a recursive relationship.
Yeah. So that's what dynamic programming refers to, using the recursive relationship between the time t and the time t plus 1. Right? And if you look at this guy here, this guy is just the same as this guy, but substituting s prime instead of s. And so this entire thing just boils down to this one, with it being replaced by s prime instead of s. So we now have the value at the state s in terms of the value at the state s prime. Right? This a backup diagram would just help you visually understand the concept much better. These are the various symbols that are used in the case of a backup diagram. As you can see, the empty circle denotes a state value. The filled circle denotes a state action value. This denotes an action, and these guys denote the maximum action value. And this is the state transition from one to the next state after the state action value. So this is the state action value, this is the next state, and this is the state transition. So a backup diagram would look like this, because we have a state, actions, state action values, multiple states, rewards that are possible, right? This would be a backup diagram for dynamic programming, and this just helps you visualize it much better.
What's the state action value?
The state action value is called Q of S comma A. That is the reward that the agent receives by being at the state S and performing action A.
What's R?
R. Okay. I'm not. R would be the reward, but the state action value should also denote the reward. Oh, right, sorry. So the state action value is for multiple actions, and the reward is just for one particular action, right? I think. So by performing this action, the reward that it receives and goes to the state S prime. That is just for this particular action, whereas state action values are for multiple actions.
I think now we go into the state that you take one action and it's not that you will reach one state directly. You have like multiple states you can reach even by doing the same action.
To clarify that, will we be able to find all of the different possible values through some sort of graph traversal then, so like exploring all the different.
Yeah, that's what type of programming is doing. Is instead of doing graph traversal, you're
Or exploring all these possible
you're take a graph, define a recursive relationship in the graph, and then like iteratively solve that.
Right. So these are the backup diagrams. Like I said, there's the state action value. This is also pretty intuitive. This is just the value for one particular action that the agent is taking. And I'm pretty sure this looks really similar to the value function, which was just VP, V pi of S, right? So given the state action value, how do you guys think we can predict the value function for a particular state? Anyone?
We can sum it up for all possible actions.
Right, so we can just sum it up over all possible actions, which can be seen on this slide. We just condition it on the probability and we multiply it out to get the value of the function. Right. Now, if you knew the value function, how do you guys think we can generate the state action value? You know? Okay. We do this, where we use the recursive definition involving the next state. And this was pretty intuitive if you go back to the Bellman equation, where we are just taking one particular action. And after we take the action, we reach the next stage. So all we care about is this one and this one, right? So if you go back to this equation, we're taking a particular action, receiving the reward, and we're multiplying out by the probability of reaching that stage by this particular action, multiplying it by the value of that particular state. Right.
Why do we want to like we want to maximize the value equation, right? Like at each state. Why is it?
Again, this is also pretty useful for dynamic programming because we're conditioning it on the next stage. Because this is the next stage that we're going to, right? S prime is the next stage that we're going to. So if
I think we go back to the maze diagram and like maybe explain it.
okay. This one. So in this case, at each stage there's only one particular action that's taking place. So I don't think there would not be much difference between the value function and the state action value in this case.
If we say that at each state the possible actions are north, south, east, west, then basically you can define the Q function as like let's say you're at this particular stage and the four possible actions are north, south, east, and west. You can define the Q value as what's the reward I get if I take the north direction from this particular state. And that would be basically like 0 or whatever the state is. So that's how you can define the Q value for all the four possible actions. And when you want to compute the value function for this particular position, you just add up all these four. And the reason why we did the Bellman equation and stuff like that is because I just wrote it for one action, but what we want is to go for an infinite chain of actions right up till the end. So basically, let's say you're at this stage. So you consider the south direction. You go here and then you need to calculate another infinite chain from here. So you're kind of doing the same calculation again and again. Then when you go to this state, you have already calculated that value essentially while doing it for this value, which is why we do the backup diagram and sort of go backwards because like when you want to calculate a state, the value for any one function, while doing that calculation, you have essentially already done it for all the neighboring states as well.
There. I hope that clears. State value function, state value function, state recursive definition. Right. Um, I don't intend to talk much about dynamic programming because the main aim of this presentation was to go through Q learning. So I'll just give it good like a brief introduction of dynamic programming. The main aim of dynamic programming is to generate an optimal policy. So this mainly involves planning, and dynamic programming assumes that it knows everything about the environment and wants to generate the optimal policy given the fact that it knows everything about the environment in this case. So, and yeah, this is planning, this is not learning, by the way. Learning means exploring and learning stuff about the environment itself, but this already knows everything about the environment. Okay, so if you're at a particular stage and you want to pick one particular action, the most obvious choice would be to pick the action which generates the maximum state action value, right? So, which is pretty obvious. So we want to generate a policy that has the maximum value of the state action pair at each stage for all states. So that is pretty obvious. Like I said, this again involves the recursive definition, which we had shown previously using the Bellman equation. But in this case, we just substitute this guy with the maximum value. And if we are able to solve this equation, we can finally compute the optimal policy that is required for us in this case. So there are two tasks in this case. One is policy evaluation, and the other is there's policy evaluation, and then there's policy improvement. So we try and evaluate. So we have a previous policy, evaluate the policy, generate a new policy which provides a better policy evaluation, and we perform this iteratively till we get a fixed point for a policy. So to understand this policy evaluation, so we're assuming in this case that we already have a policy pi, and our main aim is to just evaluate the policy. What do we mean by evaluate? Evaluating the policy just means generating the value function for each particular stage, right? Again, this has already been, like, I've already explained why this works and this equation from the previous slide. So, right. In order to evaluate the policy, we generate an infinite sequence of values which would converge to the value of the function, a value of the particular state. So how we do this is, again, we substitute the rest of the things inside the state st plus 1, and we have this stage right now. So we substitute the previous value of vk that we had for state st plus 1 in order to get the k plus 1 value of the state. So after we generate such values of vk, as k tends to infinity, we would have it converge to a particular value, and that value would be the fixed value of the particular stage for that particular policy. Does that make sense?
I guess last time you said so now states, like that's what makes sense.
No, k is not the state. K is like an approximation of the value at that particular stage. So of the value, so okay, so our main aim is to compute V pi of S, right?
Yeah.
Right? Given a policy pi, we're trying to find the value at that particular stage.
Yeah.
So we do that by having an infinite sequence of V naught, V1, all the way to V infinity that converts to this value.
So, you mean if the actions taken to come to that state as, or like what is the subscript?
Oh, the subscript. So it's like a so it's it's like a sequence which would converge to what we want to get.
So it's just like some sequence that is going to generate.
And it's generated by this recursive equation,
Okay.
right? K plus 1, sorry, K plus 1 and K.
Okay. So we define this equation and then as it is infinity, we go to conversion.
Yeah.
And that's the state actual value of that stage.
Yeah.
Okay.
No, not the state. This is the value function that we're talking about, not the state action value function.
So the expected sum or the sum of everything.
Yeah,
Okay, yeah.
that one, just that one. Anybody else has anything? Okay. So, right. So now we have evaluated the policy. Now we're trying to generate a better policy from the current policy that we have. In order to do that, let's say we have a particular policy. So now this policy pi prime of S gives us a much better reward, a total like sum of values compared to the policy pi. And in order to generate the new policy pi prime, we would just take the maximum value of the action QP of S at each particular stage, and we generate the new policy pi prime. And again, we keep updating the policy till the time it converges to an optimal value. And at this stage, we're done. So this would help us generate the new policy pi. So just to summarize, we have a policy, evaluate it, find the value VP naught, update it, improve it to generate a new policy pi1, evaluate it again, get this, improve it, evaluate till the time it converges to a particular value to get the optimal policy pi. So that was dynamic programming. I'll just give a brief introduction to Monte Carlo methods. Honestly, I don't think I have time for this. So the main part about Monte Carlo methods is that we're trying to update the value of a particular stage with this value right here. GT in this case denotes the expected return from this particular stage. And V of ST is the current estimate that we have of the value of the stage. So one thing that we need to note is that Monte Carlo methods are used to obtain the value of this particular stage, right? So we're trying to keep on updating the value of the particular stage in order to obtain the actual value of the particular stage for a fixed policy. So so the way this works is in order to obtain the GT, right? GT, which was the sum of all the, which was, this was GT, right? In order for us to obtain GT, we take one full episode of the agent from the start to the finish line in order to obtain a value of GT. And we multiply it by alpha times this in order to prevent overfitting. That's why we don't just update it with the value of GT, but instead multiply it by alpha. Because we would be performing several such episodes of the agent from the start to the finish line with multiple values of GT, such that finally the value actually converges to the actual value that we need. This is Monte Carlo methods. Again, I'm not going to be spending much time about in these two.
So these are just ways to like avoid the infinite recursive calculation, to like find the actual value. We already explained like the actual mathematical expression behind the value.
Right. So let's talk about another form of estimating the value at a particular stage. It is called temporal difference learning. So right now we're trying to evaluate the value at a particular stage following a particular policy pi. So so in the Monte Carlo method, right, we were waiting for the agent to perform one particular episode from the start to the finish line, and the agent can perform multiple episodes, which would help us get the value of GT. Whereas in this case, in temporal difference learning, we only need to wait until the next step is performed for us to update the value at a particular stage. So this is a way in which we update the value at a particular stage. Our target here is a reward at t plus 1 plus gamma times the value of st plus 1. So like I said, we just care about the value at t plus 1. So after the agent just performs one step, we can continuously update the value at a particular stage. So this is the update equation for temporal difference learning. And this can be thought of as how temporal difference learning is actually performed. We have the old value, we perform an action, takes us to the new stage, and then we finally update the old value in order to generate the new value at that particular stage. This would help us update the value at a particular stage. So temporal difference learning can be thought of as a combination of dynamic programming and Monte Carlo method, because like dynamic programming, it depends on the value at the next state as well. And therefore, it is a form of dynamic programming. And it also uses Monte Carlo methods because it uses an estimate of the value of st plus 1 as well. Just like in Monte Carlo methods, where we were trying to estimate the value of GT in that case. So TD can be thought of as a combination of both. We can skip this. This is the code implementation for temporal difference learning. So we take an action, update the value, go to the next stage, and we repeat this until we hit the final stage. We can skip this. Sure. So this was intended to help you guys understand temporal difference learning, but we don't have time. So let's skip this. So we can summarize TD versus MC in this graph. TD compares the value at the particular stage to the value at the next stage, as can be seen here. Whereas MC compares the value at the particular stage to the final total outcome. So this would help you understand the difference between TD and MC. So finally, let's try and understand what Q-learning is. Q-learning is a form of temporal difference learning, and it follows this update equation, where we have the maximum value. So again, we use the value at time step t plus 1, and we use the maximum action, which can generate us the maximum action, state action value, and we update it to get the state action value of that particular stage. This would help you understand Q-learning. So we have an agent which starts from here and wants to reach here, has several holes in between, and the main aim of the agent is to avoid the holes that are there in between. So this was the goal, the holes. So the various stages inside Q-learning would be to identify all the possible states that there are. That is, all the possible situations the agent might encounter. Identify the actions that the agent can take. So the agent can move left or move down in this case. Then we initialize a Q table. The Q table helps us understand the state action value at each particular state and action. So each row would correspond to a particular state in the environment, and each column would correspond to a particular action the agent can take. We first initialize the Q table, and then we update it using this value. Right. And like I said, our main aim was for the Q value to converge to an optimal value. So in this case, it does converge, assuming that we have explored all the particular states and actions. And if not, we use something known as epsilon greedy, in which we choose this guy with probability 1 minus epsilon, and we take a random action in order to complete our exploration with probability epsilon. So this is known as epsilon greedy. This would help us explore all the possible states. Right. And now there's the updated Q table, and we use the maximum value of the Q table at each stage in order for us to know which state the agent must go to. This is the code implementation of Q-learning. So this was the update equation in our case for Q-learning. And we repeat this until we reach the final stage in which S is terminal. Right. Finally, let's just talk about some applications of Q-learning. This is robot navigation, and this is for robot manipulation. And Q-learning can be used to help robots navigate their environment or helps robot perform certain actions. And yeah, that's it for the presentation.